Dear students, so let us see this problem. So on this frame, this is a fixed pulley. So two masses are connected by a string, and here there is some friction whose coefficient is given by mu here. And when this mass m2 moves by a distance of L, we are supposed to find out the speed which is attained by these bodies. So this problem we can try to do in three methods. So let us see the first method of solving this problem. So here we are trying to solve by using Newton's laws of motion. So let us draw the free body diagrams of this mass m1 and this m2. On m1, if I see two forces are acting, one is tension, another one is friction, which is acting in opposite direction. So if these bodies are accelerating in this direction, definitely I can say here tension must be greater than friction which is acting. So therefore I can write, so T minus mu s m1g, mu s n, here n value is m1g, so directly I am writing, is equals to m1 into a. So from this I can write T is equals to m1a into, m1a plus, so mu s m1 into g. So let it be my equation number 1. Similarly, I can write a free body diagram for mass m2 also. For mass m2, tension is pulling mass m2 upwards and m2g is acting downwards. So as body is accelerating downwards, m2g must be greater than tension. So I can write, so m2g minus tension is equals to m2 into a. From this equation, again I can write equation for tension. So T is equals to m2g minus m2 into a. So this should be my equation number 2 here. So now if I equate these two relations, then what I will get? I will get m1a plus mu s m1g is equals to m2g minus m2 into a. So if I take a common, then I can write m1 plus m2 is equals to m2g minus mu s m1 into g. So therefore a is equals to, so g if I take a common, then I can write m2 minus mu s m1 divided by m1 plus m2. So this is my equation of the bodies with which they will accelerate downwards. So now I can use the relation of v square minus u square is equals to 2as to find out the final velocity of these bodies. So v square minus u square is equals to 2as. So therefore v square is equals to initial velocity of these bodies is considered 0. So 0 plus 2 into acceleration relation g into m2 minus mu s m1 divided by m1 plus m2 into, so instead of s here I can write L as the bodies are finally moving by displacement of L. So therefore v is equals to square root of 2gl into m2 minus mu s m1 divided by m1 plus m2. So this is how I can solve the final velocity of these bodies. Also I can do the same problem by using a second method also. So that is by using work energy theorem. So work energy theorem. So it says that the work done due to all the forces should be responsible for change in kinetic energy of the body. So here, how many forces are present here? Force due to tension is present, force due to acceleration due to gravity, that is force due to gravitational force is present, and work due to friction is also present in this condition. So therefore I can write work done due to gravity plus work done due to tension plus work done due to what is the other force? Friction. So totally should be equal to K final minus K initial. So in this condition K initial is 0 because both the bodies they are in rest position initially. So now work done due to gravitational force. So gravitational force is doing work only on mass m2 here, because mass m1 is displacing in this direction and acceleration due to gravity, that is gravitational force, is acting downwards. So angle between these two is 90 degrees. So work done by gravitational force on this mass m1 will be 0, because work done W is equals to Fs cos theta and theta value is 90 degrees. So work done due to gravity is present only on mass m2. Mass m2 is coming down by distance of L, and its force acting on mass m2 is m2 into g. So force is downwards, displacement is also downwards in this condition. So work done due to gravity will be positive. So therefore I can write m2g into L. Now work done by tension will be 0 if I take both this system of m1 and m2, because on m1 tension is acting in one direction, displacement is also in the same direction. So here work done by tension on m1 will be positive. But if I take m2, tension is pulling this body upwards, but body is displaced downwards. So here equal amount of negative work is done on mass m2 by tension. So work done here by tension is positive, work done by tension here is negative. So total work done will be 0. So work done due to tension will be 0, or I can say if there is no relative motion between these two bodies, then definitely I can say that work done by internal forces must be 0. Or if distance between these two bodies is not increasing, then definitely I can say work done due to tension will be 0. Next, work done due to friction. So body is moving in this direction, friction is acting in opposite direction. So definitely friction is doing negative work in this condition. So therefore plus minus of mu s m1 into g into L. So this is a frictional force, this is the distance traveled, force into displacement will give work done. So this is equals to change in kinetic energy. Initial kinetic energy is 0, but finally both the bodies are attaining kinetic energies of half m1 v square plus half m2 v square. So these are the final kinetic energies, as initial kinetic energies are 0. So therefore the equation which we got here is, so m2g into L minus mu s m1g into L is equals to v square by 2. If I take common, then it is equals to m1 plus m2. So gl and 2 I take on one side, then again I will get the same relation, v is equals to square root of 2gl into m2 minus mu s m1 divided by m1 plus m2. So by using method 1 also we got the same relation here. Now the same equation I can also calculate by using method number 3. So in third method we try to solve by using law of conservation of energy, which we have not discussed until now. So law of conservation of energy. So here I can say, so as this body m2 is coming down, it is losing some of its potential energy, because when it comes down by L, then it is losing a potential energy of m2g into L. So this loss of potential energy should be converted into kinetic energy of both the bodies, as well as some of the work is done converted into work done due to friction also. So therefore I can say the potential energy lost by m2 can be written as m2g into L is equals to, and the kinetic energy gained by both the bodies is how much? It is equals to half m1 v square plus half m2 v square, and work done against friction is equals to mu into m1 into g into L here. So again, if I solve the relation for velocity in this condition, then again I will get the same relation. V is equals to square root of 2gl into m2 minus mu1 m1 divided by m1 plus m2. So by these three methods we have done this problem here. So any one method we can adopt to calculate here, but we are supposed to learn all these methods, as each of these methods will become easier depending on the type of problem which we are solving in. So this is a wedge which is moving, which is accelerating in this direction. So here a spring is attached here, and to this spring a mass of L is being attached in this condition, and there is a frictional force present between this mass and this. So let a block is having a mass of m, and friction exists between this block and this wedge here. So block slides by a distance L relative to the wedge, then find maximum deformation of the spring. So if this wedge is accelerated, spring is elongated by a distance of L, then we are supposed to find out deformation. Deformation is nothing but L value we are supposed to find out here. So this problem I can solve by using work energy theorem. So what is work energy theorem in this condition? So total work done by all the forces should be equal to the change in kinetic energy. So I am doing this problem from non-inertial frame of reference. So that is, I think that I will take observer to be present here. So before this block was accelerating, the block was in rest position, and after accelerating, then after reaching a maximum displacement of L also, then also the block is in rest position with respect to the wedge. So this observer sees that initial kinetic energy and final kinetic energy of this mass is always 0. So therefore I can say, so the different works done here due to different forces which are acting are, so work done due to spring plus work done due to gravitational force plus work done due to pseudo force plus any other force which is present here, spring force, gravitational force, pseudo force, and any other force is it acting in this condition. So work done due to friction is also present. So work done due to friction, because here there is a coefficient of mu here. So total should be equal to delta K, which is equals to K final minus K initial. And this K final minus K initial is 0, because with respect to this observer, this mass is always in rest position initially and finally also. Now if I take work done due to spring, then spring is elongated in this direction. So but restoring force will act in opposite direction, though therefore we know work done due to spring in this condition it is negative. So it is given by minus half K L square, where K is the spring constant of this spring. Now if I consider work done due to gravitational force, so on this body, the gravitational force which is pulling this body down the inclined plane will be mg sin theta, but body is displaced upwards here. So if I draw the diagram here, so this is the body of mass m. So mg sin theta is the component of gravitational force parallel to the inclined plane, and here I can say this is the displacement L of this body. So both of them are at an angle of 90 degrees, so definitely work done due to gravitational force will be negative. So therefore work done due to gravitational force will be minus mg sin theta into L in this condition. Now I will consider work done due to pseudo force. So if I take this body, as body is accelerating in this direction, observer is also accelerating in the same direction. So pseudo force will start acting exactly in opposite direction, which is MA. So if this angle is theta, then definitely I can say this angle also will be theta. This MA I can split into two components. So I can split like this. So this will become MA cos theta and this will become MA sin theta. So the component of pseudo force in the direction of displacement is MA cos theta, and displacement also is in the same direction. So therefore work done due to pseudo force will be positive, and it will be MA cos theta into L. Now we will calculate work done due to friction. Okay. So work done due to friction will be definitely negative in this condition because body is moving upwards. So friction will act in downwards direction. So work done due to friction I can write out minus mu s n into L. So this is the frictional force, this is the displacement. So force into displacement will give work done. Now the question is, what is the normal reaction in this condition? So if I observe here, definitely I can say mg cos theta is pushing the body, this is the force with which this body is pushing this inclined plane, and normal reaction will be acting exactly in upwards direction. So there is one another force which is pushing this inclined plane, that is MA sin theta also. So this MA sin theta and mg cos theta should be equal to normal reaction. So therefore normal reaction must be equal to MA sin theta plus mg cos theta. So if I write work due to friction, then should be equal to minus mu s into MA sin theta plus mg cos theta into L. So now if I add the work done due to all these what you called works done, then I can write like this: minus half k L square work done due to spring, and work done due to gravitational force is minus mg sin theta into L, and work done due to pseudo force is MA cos theta into L, and work done due to friction is minus mu s into MA sin theta plus mg cos theta into L, and totally it should be equal to 0 because this observer does not see any final velocity for this body of mass m. So this square L and L gets cancelled. So if I rearrange this relation, then the final equation for here in L square, only square gets cancelled, L will be present. So the equation of L which I must get here is L is equals to 2m by k into a into cos theta minus mu sin theta minus g into sin theta plus mu cos theta. So this is the relation which I have to get. So I hope you can solve from here onwards. Dear students, so let us see this problem. So a particle moves in a straight line with retardation proportional to its displacement. Then the loss of kinetic energy for any displacement x is proportional to which of them? So loss of kinetic energy, that proportionality, it is proportional to which of these values that we are supposed to find out. So here the given condition is that retardation, that is I can write A, is proportional to minus x. So this is the given condition. So this I can write. So if I want to remove this proportionality symbol, I can place a constant. So A is equals to minus kx, and so this is how I can write. So loss of kinetic energy he gave. So this equation, how can I convert in terms of loss of kinetic energy? So loss of kinetic energy depends upon change of velocity of the body. So from acceleration, how can I calculate in terms of equation for velocity? So we have two equations for acceleration. One is A is equals to dv divided by dt. This relation I have. Similarly, I have v dv divided by dx. So previously many problems we have done based on this relation. So here this relation I cannot use because acceleration is not changing with respect to time. Acceleration is changing with respect to displacement here. So I will use the relation A is equals to V dV divided by Tx. And it is given as minus Kx. So this equation I can write V dV is equals to minus Kx into dx. This is how I can write this relation. Now, if I integrate this one on both sides, then what will be my limits of integration? So, as the kinetic energy is decreasing, so limits of integration will be v1 to v2. So, initially if the velocity of the body is v1, finally its velocity is v2, so the limits will become v1 to v2. And here x value it is changing when I started observation, then I will consider x value to be 0, and after some time the x value is covered is x here. So this is how I can write. So therefore we will write here, so integration of v square will be v square divided by integration of v dv, v square divided by 2, and the limits are applied from v1 to v2. So this is equals to minus k. If I take common, then I have x dx. Limits are applied from 0 to x. So this value is equals to minus k x square divided by 2. And if I apply the limit 0 to x also, I will get the same relation. So now here if I substitute the limits, then I will get it as half. If I take a common, then I will get v2 square minus v1 square is equals to minus kx square divided by 2. So I got the equation up to here. But still I have no information about kinetic energy. So this relation, if I multiply by m, then definitely we know it converts into the change of kinetic energy. So I will multiply by m on both the sides. So therefore I can write half into m into v2 square minus v1 square is equals to minus m kx square divided by 2. So now this relation is nothing but a change in kinetic energy. So this change in kinetic energy is proportional to x square, because mass k and 2 they are constants. So this is our answer. So option A should be our. So let us see this question. An elastic spring of natural length L and force constant K is stretched by a length alpha. It is further stretched by a length beta. Then what is the work done in second stretching? That is the question. So let us see how we can solve this problem. So consider this is the natural length of the spring. So from here, if we are stretching the spring up to here, that is by a distance of alpha. So this distance is alpha. Then from here onwards, again I am stretching by a further distance of beta. So if this is alpha, then this value is again beta. Then the question is, what is the work done in the second stretching? That I want to calculate. So for case number 1, the work which we have done in stretching the spring, that will be stored as potential energy inside the spring. So therefore, the energy stored in the spring can be written as half k alpha square. So this is PA1. Similarly, to stretch a complete length of alpha plus beta, the amount of work which we done, it will be again stored as potential energy 2 in the spring, which I can write it as half into k into, now the total stretching is alpha plus beta whole square. So this is the amount of work done by the external force, this is the amount of work done by the external force in second condition. So therefore, the amount of work done to stretch from alpha to beta can be easily obtained by W2 minus W1. So which is equals to half k into alpha plus beta whole square minus half k alpha square. So here if I take half k as common, then I will get alpha plus beta whole square minus alpha square. Okay. So this should be equal to, so half k into, So this, if I expand according to the equation of a plus b whole square, then it is alpha square plus beta square plus 2 alpha beta minus alpha square. So this is equals to half k into, so this alpha square and minus alpha square gets cancelled, and here if I take a beta as common, then I will get beta plus 2 alpha. So this should be our answer. So therefore the additional amount of work done to stretch from alpha to beta, delta W is equals to half k into beta plus 2 alpha. So this should be our answer. Dear students, so let us see this problem. So if the kinetic energy of a body is directly proportional to time t, then the magnitude of force acting on the body depends on which of these values. So this is a multi-correct type of question. So out of these 4 options, 2 options are correct. So those we are required to identify. So let us see how we can solve this problem. So kinetic energy is proportional to time t. So let us write that one. So kinetic energy is proportional to time t. So for removing this proportionality constant, I will symbol, I will place a constant. So kinetic energy is equals to what constant can I write? I will write P into T. So kinetic energy is equals to P into T. Then how can I relate this kinetic energy to force? So we have work energy theorem, which says that work is equals to force into displacement is equals to change of kinetic energy. So initially, if the kinetic energy of a body, if I assume to be 0, then I can write kinetic energy is equals to P into T. Here this I can write. So and force can be written as mass into displacement in this condition. So force into displacement can be written as P into T. Then displacement again I can write it as half AT square. So force into half AT square is equals to P into T in this condition. So again A can be written as F by M also, because I am supposed to find out the relation between force and these required values only. So therefore I will write F into half into, instead of acceleration I can write F by M into T square is equals to P into T. So what I got F square divided by 2M into T square is equals to P into T. So this is the relation which I got. So now have this F square on one side and take all the remaining terms to the other side. So F square is equals to P into T into 2M divided by T square. So by looking at this equation, definitely I can write F square is equals to P into 2M divided by T. So by observing at this relation, definitely I can say F square is proportional to 1 by T, because P is a constant and M is also a constant in this condition. So therefore I can write F is proportional to 1 by root T. So this should be my first answer. So therefore option B is correct here, inversely proportional to root T. So now if I try to solve what is the second option, let us write the same relation again here. So F square is equals to P into 2M divided by T here. So from the first equation of kinetic energy, I have what I have P into T is equals to kinetic energy. Kinetic energy can be written as half mv square here. So therefore from this relation, P into T is equals to half mv square. So this I can write T is equals to half mv square divided by P. So T is equals to mv square divided by 2P. So now I will try to substitute this relation in this condition. So F square is equals to P into 2M divided by, instead of T I can write mv square divided by 2p. So therefore I can write 2p square into 2m divided by mv square. So here f square is equals to 2p square into 2m divided by mv square. So here I can see that p is a constant which we have assumed, mass is a constant, here also mass is a constant. So therefore I can write f square is inversely proportional to v square. So therefore f is inversely proportional to v. So this should be my answer. So my another option is inversely proportional to speed of the body. So these are my two options which I will get. So dear students, let us see this question. So two blocks A and B have masses m and 4m respectively. So each one is acted upon by a force of F. If they acquire same kinetic energy in times TA and TB, then we are supposed to find out the ratio of TA and TB. So let us take this is one block of mass m. So this is acted upon by a force of F. So we have another mass 4m, so which is also acted upon by the same force. Now it is given that both of them acquire same kinetic energy. So kinetic energy for this one, if it is Ke1, kinetic energy for this one, if it is Ke2, then it is given that Ke1 is equals to Ke2. So these two are equal. So this amount of force will do a certain work. So that can be written as work is equals to force into displacement is equals to change in kinetic energy, which is called work energy theorem. So here the initial kinetic energy is 0. So only we have final kinetic energies which are equal in this condition. So for first body, how can I write the relation? I can write W is equals to force into displacement is equals to K, because Ke1 and Ke2 both are equal to K. Here I can write. So W is equals to force into displacement can be written as half AT square, because as force is applied, these bodies will accelerate. So this is equals to K. And we know A is again equal to F by M. So F into half into A is equals to F by M into, instead of T I can write TA square, that is time taken for body A to gain the same kinetic energy as equal to body 2. So this is equals to K I can write. So therefore I can write F square divided by 2M into TA square is equals to K. Now similarly I will write equation for second body when same amount of force is applied. Here also work done is equals to force into displacement is equals to K final, or just I can write K also here. So W is equals to F into half into A into T square is equals to K. So W is equals to F into half into, in this condition acceleration A is equals to F by 4m. So into T square, here now I will write instead of T I will write TB square, time taken for body B, and this is also equals to K. So therefore W is equals to F square divided by 8m into TB square is equals to K. So let it be my equation number 1 and let it be my equation number 2 here. So I want TA by TB. So here I have TA square, here I have TB square. So let us divide these two relations. So if I divide these two, then F square gets cancelled. Then the relation which I will get is TA square divided by 2 divided by TB square divided by 8 should be equal to 1, because kinetic energy in both the conditions is same in this condition. So TA square divided by TB square is equals to, and here I can multiply with 8 by 2, so this equals to 1. So TA square divided by TB square is equals to 2 by 8 is equals to 1 by 4. So therefore TA by TB is equals to 1 by 4 whole square, which is called 1 by 2, and this should be my answer. So therefore the ratio of TA by TB is equals to 1 by 2.